Okay, so if recursion is not coming easy to you, don't worry. I wouldn't be too worried about it. I would just say definitely try to set up as many recursive functions as you can. Now, there will always be times when you might make mistakes and you end up with what is called infinite recursion. And so in C++, you want to be ready for this. If you don't ever get to the base case for whatever reason, then what you can end up with is infinite recursion. That is, recursive calls never end. Well, will it go on to infinity? No, it's not like an infinite loop. Why is that? Mainly because every time a function calls another function, even if it's the same function, that is in recursion where a function calls itself, you need a tiny bit of space to do that recursive call. And if a function calls itself many times, eventually you will run out of memory. And so the program actually ends up crashing. So let's set up a recursive function that, let's set it up purposely so that it doesn't end. It's not that really not that hard to do. What's hard to do is to figure out that you have this situation. Okay, so let's set it up. Here's the simplest possible recursive function. You just call a function f. You have to define it. So you set up a simple void function, right? So far so good. Doesn't look anything out of the ordinary. But here's how you can set up infinite recursion, which is not useful. This is definitely not something that's useful to do. You can do this. You call a function f. This function has no parameters and it just calls itself. What can you expect if you have a function like this? So this is the way to have unsuccessful recursion, and you want to recognize why recursion might be unsuccessful. So if you run this, what happens is it runs and then it terminates, and you get no error messages, nothing. All you know is that if you can see over here, it says terminated. It prints out this first line of output that came from here, and that was it. After that, there's nothing. So here is a better thing to do. You want to call this recursive function with some kind of input. So it doesn't matter what. Let's just say we give it the input 4. Okay, and then we can do anything we want with this, but let's say we're going to set up this function, int n. And what we're going to do is we're going to print it out. Cout n and len. Okay, and let's see what happens. And notice to have a successful recursive function, you do need a situation where the recursive function calls itself with a smaller version of the original task. And also finally, you do want a base case. And this example that we're setting up, we're purposely not setting up a base case. So far we didn't set it up with a smaller version of itself. What is a smaller version of a number n? It's just decremented, let's say. All right, so that's good enough. But we know that this is not going to be successful because we don't have a base case yet. So let's compile it. The compiler won't warn you that you have infinite recursion. It'd be nice if the compiler could figure that out. But here you can see that you start at 4 and you keep going, you have a function that calls itself roughly 200,000 times. And that's it. It terminates. Okay? So one base case would be we don't want it to go negative. So just giving you a setting up. This doesn't really do any useful work. Just it does a countdown, I guess. If n is equal to, or let's say less than or equal to 0, we just return. So that one simple if statement without any recursion is our base case. So this is our base case. This is where we break the problem down into a smaller problem from n to n-1. Okay. So I can compile this as before, no warnings or anything. But this time around, when you run it, you do actually just get a simple countdown. You start with 4. When you call it with 4, the function calls itself with 3 and -1. So 4 minus 1 is 3. Then when you have 3, you print it out and you call yourself with 2 and so on. So you can see how this works. So if you're trying to figure out how recursion works, check and make sure you understand this much simpler example where you actually don't really accomplish anything. You just set up the mechanics of recursion, of successful recursion. That is, you break a problem into a smaller problem, but very similar one, and you set up a base case where you can use, you can do something without any work, without any recursion, and you do something. In this case, you just return. Okay. All right. So try out that example so that you can recognize situations where you have runaway recursion. What you can do is comment out this if statement, and then you'll see that you get a runaway recursion. It goes, n becomes negative and becomes sort of a large negative number, and eventually runs out of space. And from that you have some estimate of how many times a recursive function can call itself. Of course, it'll depend. If you have variables in here, each time you call yourself, it needs more memory if you have variables, and so it won't be like it's always going to fail after 200,000 calls. So, but in this case, oops, let's comment it out, compile it, and run it. And we see that in this case, you get to call a very simple recursive function about 262,000 times. That's the limit in this 32-bit system. Of course, if you have a different operating system with more memory and things like that, you could go even more. You could go even longer than 262,000 recursive calls. Okay, but that gives you a rough idea. After a certain number of calls, it's going to stop because you've run out of space. It doesn't go to infinity. Okay, so consider this alternate function definition. So what you do is you say void, as before, this new right vertical function where you get an input parameter, and here you cut down the problem size by 10 and you print it out. And it sounds reasonable, looks reasonable, but as we saw in our simple example 2, this is missing a base case. You need that if statement, and because of that, the recursion never stops. You might want to try it out and see what happens. See if you can see if the compiler will warn you that you have infinite recursion. It doesn't, and just check it out for yourself, and then run it. And what you will see is that it prints out a certain number of things that make sense, and after that, it doesn't really make sense. Okay. So it turns out the way recursion works in just about any programming language, any modern programming language, is to use the stack. A stack is a specialized memory structure. It's like a stack of paper or a stack of trays in the cafeteria. I guess they don't have trays anymore these days. But it's a stack of things, and a very specialized data structure where you can only place new things at the top of the stack and only remove if you have to remove something, you can only remove from the top of the stack. And this is called last in, first out. That is, the last thing that you put on the stack is the first thing that you take out of the stack. Okay, so it's also called LIFO, that's abbreviation of last in, first out, LIFO. So a LIFO memory data structure. Recursion uses stacks. So this is provided by any operating system. You get to use a certain amount of stack space, and there's support for using stacks at the processor level. On the CPU, there's actually machine language instructions for pushing and popping onto the stack. Pushing is putting the last thing at the top of the stack. Popping is taking the first thing out of the stack. And we'll see more about how to implement stacks and things later in that stack. A stack is a standard data structure that we pretty much all have to learn to implement. All right. Well, one last thing is, whenever you call a recursive function, that some data corresponding to that function call is placed on the stack. And when you return from a recursive function, the last call, something on the stack corresponding to the last call, is removed from the stack. So calling a recursive function adds to the stack, you push onto the top of the stack. Returning from a recursive function pops or removes something from the stack. The size of the stack is limited, and of course, since memory is finite, and so if you have a long chain of recursive calls, it continually adds data to the stack, and eventually you hit the stack limit and you get a stack overflow. And if you run a lot of programs, if you run from the command line, you would see an error message, but in Eclipse you don't actually see an error message, it just says terminated. And you can count how many times this function was called recursively. It was about 262,000. So it gives you some idea of how many things you can put on the stack. So if you have infinite or runaway recursion, is how I call it, it always causes this stack overflow, and unfortunately in Eclipse you don't get an error message. In Java you do. So when we learn recursion, almost always what we do is we solve problems that we could just as well solve using iteration. So you might say, well, do you really need recursion? Turns out, no. Recursion is not always necessary. Some languages don't even allow recursion. There's a lot of languages that used to not allow recursion, and these days it's just assumed that everybody will want to use recursion, and so most programming languages today will allow it. It's not that much work in a language to support recursion. Any task accomplished with recursion can also be done without it, non-recursive, that is using loops, and that's called iterative solutions versus recursive solutions. So there are problems with recursion. It runs slower, it uses more storage, that is the stack space. You don't need anything like a stack space for iteration. All you need is an int counter. Often that's enough for int I equals 0, I less than whatever, 100,000, I plus plus. You just need that one int, whereas if you had to make 100,000 recursive calls, you'll use up about half your stack space. So an iteration uses very little. However, even with all these disadvantages, the main advantage is that you can come up with very nice, elegant solution using recursion, and we'll see this for sure later on when we use trees, that you get the solution is so simple that there's no debate. Recursion is the way to go for a lot of problems, for a lot of complex data structures, just because it gives you less coding, less opportunity for bugs and things like that. So once again, right now we will solve problems with recursion that we could just as well solve using iteration, but pretty soon we'll see that recursion gives you some very nice solutions. You cannot have those solutions with iteration.